Okay, let's look at the general structure of recursion, and we'll look at one more technique for analyzing recurrences. So imagine that we've got a general recursive algorithm, and this is very typical of many recursive algorithms. So it's going to do something, it's going to be given an array of data to work with. There will be some code that checks a base case, and then some code that maybe processes all the data at this instance size. And then recursive calls. In this case, the recursive calls each deal with half the data, the first half of the data and the second half of the data. Okay, so we could actually kind of break this into up and use the terminology that we've used prior to this. So there's some amount of work that's being done at each instance of this. So we'll say that that's a f of n, a function of the problem size. And there's some recursive calls. And in this case, the recursive calls break the problem in half. So our g of n could be considered to be n over 2. Now, what's important about this is we've now introduced this idea of having two recursive calls. And we've already got kind of this generic notation to refer to the other parts of our problem, but we'll even make that a tiny bit more generic. The recurrence for this would look something like this. The amount of work that we need to do is based on the work done in those two recursive calls. Each recursive call deals with half the data, plus the amount of work that's done at each instance. Okay, I want to focus on these two values here, the two twos. So one of them is referring to the recursion, and the other one is referring to the reduction in problem size. Okay, so let's be a little bit more generic. Let's imagine that we replace those two terms with some variable. So imagine that we're going to have some recursive calls, could be one, could be two, could be many more. And we're going to reduce the problem size by some factor, but it'll be more generic than just two. Maybe we'll reduce it by 3, maybe we'll reduce it by 4, it's hard to say. So this gives us this more general form that will describe a wider array of algorithms. By the way, we will assume that small problems aren't that interesting to us right now. So the time taken on a small problem will say will be constant for small values of n. So this general form describes lots of different problems, including a couple that we've already seen. So one of the examples we've looked at in this module is binary search. So binary search is continually breaking down the problem into half of its previous size, and at each individual instance it has to do some constant amount of work. So in this case, our A would be considered to be 1 and our B would be considered to be 2. We'll also look at merge sort later this semester. So merge sort recurses in two different directions, and each time in each way it's broken up the problem into half. This is very similar to the do something method in the prior slide. And at each particular instance it has to do work on all of the data. There's also a well-known matrix multiply algorithm that follows this general form, although you'll notice that the A parameter happens to be 7 here. And there's an algorithm for finding the maximum subarray, and you'll notice that this is very, very comparable to binary search. Okay, so let's go ahead and also develop a new strategy to expand the recurrence and analyze it based on an expansion. So we'll look at an example. We'll look at an example that we just saw, essentially the recurrence for binary search. So t of n equals t of n over 2 plus c. So we could expand this. We could replace the t of n over 2 by using the recurrence itself. Replace it with n over 2 over 2, otherwise known as n over 4 plus c. So we saw an example of this earlier. So we could then expand that further, replace the t of n over 4 with t of n over 4 over 2 plus c, which is t of n over 8 plus c, and so on and so forth. So the question is, how many times would we do this? At some point, there has to be an end point. So for almost all these problems, we could assume that a problem size of 1, perhaps, has some constant known time. So we would repeat this until our fraction was essentially our base case. Okay, so thinking about that, we would repeat this over and over and over so many times until we eventually get to our base case that we know does C units of work. So it's repeatedly dividing by 2. So your intuition may lead you to expect this to be log base 2 of n. And in this case, we would consider it to be big theta of log n. Okay, so one of our goals will be to take this general form and compute the sum for any recurrence of this particular form. So one approach we can take is something we've also already done. We can draw a tree that represents the computation that's going on, and then we can do some counting on that tree. So this tree will include the recurrent terms. It'll be called the recursion tree. Node in the tree will be a record of work done for a particular term in our expansion. So it'll be work done at that particular instance of the function, or method, actually. Then our goal is to do some accounting, add up all the nodes in the tree. Okay, so let's work through a concrete example to explain what I mean by the nodes in the tree and this accounting process, just to make it a little bit more concrete. So continuing with our binary search example, so T of n equals T of n over 2 plus C. So constant amount of work at each node plus the problem size keeps getting halved. So the root is doing C amounts of work. So we'll start off with that. So we'll draw this diagram that kind of represents the computation done on the first call to this function. So the instance of all n items of data when it first starts running. Okay, and then we'll expand this out. So it'll do a recursive call with a problem size of n over 2, and that recursive call also does C units of work. So again, the value inside the nodes here is representing that local amount of work done at each node, our f of n, which here just happens to be a constant amount of work at each node. Okay, and then we'll expand that again. We'll do n over 2. We'll break the problem into half yet again, and so on and so forth. Okay. And so we can kind of generalize the form that we see here. It's dividing by n by increasing powers of 2. So 2 to the 0th, 2 to the 1st, 2 to the 2nd. In fact, we could express this kind of generically as 2 to j. Okay, so we'll go ahead and add that in. And again, the question is, where does this eventually trail off at? Well, we've already identified that we're going to consider a problem size of 1 to have a constant amount of time or a constant amount of work. So in this problem, we'll consider that T of 1 is C units of work. Okay, so this leads us to the question of how many total nodes are there here? So how many steps or links in this chain? So we can consider this based on depth away from the root node. So the first node we process itself is a depth of 0, depth of 1, depth of 2, ... Okay. By the way, to make this a little bit simpler to think about for now, we'll also assume that n is a power of 2, so that we evenly and cleanly get to T of 1. Okay, so if that's the case, then there will be log base 2 of n total steps. Okay, so let's do some accounting. We start with a depth of 0. We go to a depth of log base 2 of n. So our total amount of work will be a sum from our depth 0 up to and including our depth log 2 of n of the C units of work that take place at each individual step. Okay, so this is a sum of log base 2. So we'll be able to simplify that to C times the log base 2 of n of 1. Okay, and that would fall in the big theta of log n. Just to make this a little bit more concrete, let's imagine that our problem size were 8. So T of 8, T of 4, T of 2, and then t of 1. So in this case, this would be our final problem. So we would have a total of 4 instances of this. So the log base 2 of 8 is 3. So we'd start at instance 0 up here and work down to and including instance 3. Okay, so again, the total height here would be 4 different steps, and each one of those would be doing C units of work. Okay, so our general recursion tree approach will use a recurrence to, we'll sketch out a recurrence tree, a recursion tree. We'll identify work that's taking place at each node in that tree. We'll figure out the total height of the tree. We'll also figure out the work at each level. So we'll kind of sum from left to right across our tree. So our next example problem will look at a more sophisticated tree that's not just a simple line. So we didn't really have to worry about this step in our last example. And then we'll sum up across all of the levels from top to bottom in the tree. Okay, so let's look at another example that will address point number 4 here, needing to sum across the work that's done in a particular level. So we'll consider a more complicated recurrence. So in this case, we'll have each recurrence be 2 times t of n over 2. So we're breaking the problem in half and recurring in 2 different directions. And then at each level, we'll do Cn units of work. And this time we'll assume that when we're down to just 1 unit of work, there's a different constant for the amount of work that's done at that layer. So these kind of indicate the constant that's needed to process each item as we're recurring versus the work that's done in the base case. Okay, so we'll again go through this process of building our tree. So we'll start out at a depth of 0, and we'll create a node that represents the total amount of work that's done at that depth. Okay, in this case, it's going to recur 2 different ways. Now, we've seen this a lot as we've been looking at trees. So it'll break the problem into half. So at the next layer down, it'll do C units of work for each of the n over 2 nodes. And it will break the problem into 2 different halves. So there will actually be 2 different nodes at this level. Okay. Then we'll descend down another level. Each of those nodes that was given n over 2 units of data will have 2 children itself that have half as much data, or n over 4 units of data. So that'll break down into 4 different nodes. So if this looks familiar, it really, really should. So this is very similar to what we've been seeing with our heaps. Okay, so the process will continue on down until eventually we get down to the leaf nodes of the tree, which each do d units of work. Again, those are kind of the base cases. It's a different unit of work, potentially. So we're using a different variable to represent it. Okay, so now let's try and tally it up. So let's think about this overall tree and the problem size versus the nodes versus the work we're doing at each node. So at a depth of 0, our problem size was n. So that was that root node that was doing n units of work. There was 1 node. There was a total of C times the work at that node, C times n work per node. Moving down 1 layer, we broke our problem into half the size, but we had 2 of them. So the next layer down, we had problems of size n over 2, but 2 of them. Each of those nodes was doing its constant amount of work for the set of data it was given, the half of data it was given. So we could continue on down the tree and we can try and generalize this. So we'll try and express it in terms of a variable that represents depth. So we'll use j to represent the overall depth. And the problem size keeps going down by a factor of 2. So we can represent the problem size as n over 2 to the power of j. And the number of nodes keeps increasing by a factor of 2, so it's 2 to the power of j as we keep going down. And then the work keeps getting multiplied by c. So the work per node is the data at that node times c. Okay, and then finally the bottom of the tree we'll get to when we have gone down log base 2 of n steps. The problem size will finally be 1. We'll have a total of n nodes. And each of those nodes will do d units of work. Okay, so let's let's also think about this in terms of the work that's taking place at each level. So here's our same tree. We've got the local work per node and the number of nodes. So the product of these two is the number of things times the amount of work each thing is doing, and that happens to be Cn for the first layer. In the second layer down, we've got two nodes, but each one's doing half as much work. So the product is still going to be C times N. And as we continue down the tree, we'll get more and more nodes, but each one's doing less and less work, and the product will continue to be C of N until we get to our bottommost layer where we're doing our base case and we're not doing C units of work per node. So we'll have our N nodes, each doing D amount of work. Okay, so this is a little bit different than our previous problem. So let's focus on some of the big differences. So one of the big differences is that it's doing this C times N units of work for the 0 through jth node. But it's not going up all the way to the last level in the tree. It's stopping at the next to last level. Okay. Okay, so it will be the sum from 1 to log of n minus 1. It'll stop one layer below the last layer. Okay, and each of those layers, it's doing Cn units of work. So we can come up with a summation. Sum from our root up to our next to last layer of the amount of work in total being done at each of those layers. So again, this is a summation across the layer. If we looked back at our diagram, we could kind of circle each level of our diagram and would identify that it was doing this amount of work in total. Okay, and then we also have to factor in the amount of work that's being done at the very end on our last layer, our leaves of our tree, which is n times d. N leaves, d units of work each. Okay, so for the entire tree, we've got the amount of work that's being done at the leaves, plus the amount of work that's being done at all of the other layers of the tree. And we can simplify the summation using our rules of summation for logs. And we end up with something that is in theta of n log n.